Good morning. We are, can you hear me in the back? There it is. We're going to, the exams are graded and the grades are online, but we are not going to return them until Friday. But there's a good reason for that. Some of your grades may go up by a few points. But not down. Not down. Not down, guys. unless, yeah, not down. Okay, we talked about anionic and cationic polymerization, and particularly what makes a substrate better for either cationic or anionic polymerization. And we talked about the difference between electron donating groups and electron withdrawing groups that make one type of vinyl monomer more susceptible to either cationic or anionic polymerization. And it's not perhaps quite clear why a particular X group would make an alkene or double bond more reactive toward either positive or negative charges. So I want to give you a little bit of a primer on alkenes. An alkene is just a carbon-carbon double bond. So a lot of terminology we kind of use a little bit interchangeably. An alkene is just this. If it's this with something on it, it's a vinyl group. Now, a vinyl monomer, if you look at it in terms of molecular orbitals, what you have is carbon-carbon, then we have hydrogen atoms. Here we have the X group here, and these carbon atoms are sp2 hybridized, which means that they have these pz orbitals, these p orbitals that interact to form a pi bond. Whereas the single bond along the internuclear axis is the sigma bond. Now, the pi bond is not as strong as the sigma bond. What it does is it restricts rotation along the between the two atoms that are bonded with the pi bond. But you also have this cloud of electrons above and below the internuclear axis that can react with radicals and also charges. So in the case of radicals, what we have for a vinyl monomer is really a resonance structure where one of the electrons of the pi bond can go to the terminal carbon atom, and one electron can go to the interior carbon atom. So you can think of this vinyl monomer as being in resonance with this structure where the two electrons are separated. And what happens when you have an initiator fragment, or sometimes we call it I dot or R dot, depending on if we need R for something else in the reaction, what happens is that the more reactive radical is on the terminal carbon atom, and the more stable one is on the interior carbon atom. In general, radicals and charges are more stable on the most substituted carbon atom. And the reason is because radicals and positive and negative charges exist in an unhybridized p orbital in an sp2 hybridized carbon atom. And if they're in this p orbital, they can delocalize to other atoms in the system. So if you have the more substituted carbon atom, the radical can delocalize more easily. That's why the reaction proceeds off of this carbon atom after the initiator fragment reacts with the end. So this is for radicals. Now, what about for cationic polymerization? What you need is an electron-rich alkene where our X substituent needs to have either a lone pair or pi electrons. And usually pi electrons in a CC double bond. So what happens is that this structure you can think of in resonance with as a superposition of this structure and a structure in which the electrons are shifted in such a way to produce a formal positive charge on the X group and a formal negative charge on the terminal carbon atom. So if we have a positive charge due to our acid that we've added, either our methane sulfonic acid or H2SO4, or even better would be a Lewis acid where we've doped in a little bit of water, that this negative charge, this pair of electrons, will form a bond with the hydrogen. And then we go from this resonance structure to this structure. But usually the positive charge on the X group probably does not have an unfilled valency. The atom that now has the valency that wants to be satisfied is this one. But this structure is in resonance with the structure in which this pair of electrons now satisfies this positive charge, and we end up with the positive charge on the more substituted carbon atom. And this is the carbon atom that then reacts with the next monomer. So really what we've done, this is just kind of the mechanism of the first step in the cationic polymerization. So yeah.
A question about the sharing of electrons. So we have the pair of electrons that forms the pi bond, balancing out a single positive charge on the X nucleus. Is that because when the X nucleus is sharing a pair, it's only really taking charge credit for one of the electrons' charge?
Do you remember formal charge you can calculate what charge gets what atom. You take the number of electrons in the free atom minus the electrons in the lone pairs minus the number of bonds, and that gives you the formal charge on every atom. And if you do that for any of these reference structures, you'll get -1, 0, and +1 here. If the X group is if we have these lone pairs to begin with, like oxygen. So in this case, X, the identity of X is always going to be OR, or not OR again. It's going to be OR or some kind of C double bond C. It could also be NR2. In fact, polyvinyl carbazole, which is a holographic material, is made by cationic polymerization, as is essentially all polyisobutylene or butyl rubber, which is what car tires are made of. Those are really by far the most prominent examples of materials that are polymerized by cationic polymerization. In the case of polyvinyl carbazole, it uses the NR2 group. So vinyl carbazole, this is just for fun, don't need to know this. This is used in holograms, so you polymerize here using a cationic mechanism. And in this case, the lone pair comes from the lone pair on the nitrogen atom that stabilizes the positive charge here once you add acid to the system. Okay, for anionic, instead of something that donates electrons into the system, we need something that sucks electron density away, because we need this carbon atom to be reactive toward negative charges, not positive charges. So for anionic polymerization, we need electron poor alkenes. And I'll draw this as X, but X always has a particular structure. It's essentially always a carbon atom. So what I'll do is I will draw this as a carbon atom connected to something called Y. And Y is an electronegative atom. So X is just the C double bond Y. That's what X is here. So Y is an electronegative atom. Usually oxygen or nitrogen. And what it does is it sucks electron density toward it. So this structure is in resonance. Again, it's really a superposition of this structure and also a structure that sucks this electron density toward it. So we now have Y with a formal negative charge and a formal positive charge on the carbon atom. And remember, we were talking about alkyl lithium reagents where the R group has a formal negative charge. It then reacts with the positive charge in this version of the resonance structure. This is sometimes called 1,4 conjugate addition or Michael addition, if your name is Michael. And you don't need to know that. You know, sometimes the horridness of a joke is worth the laugh just because it was horrible. Anyway. Okay, so we now have this R group bonded. And what we have is our Y group with the negative charge, double bond, single bond, and now bonded to the R group. So the negative charge then moves up the chain to regenerate the vinyl monomer that now has the negative charge where we expect it to be. So this structure is now in resonance with this. And this is now where what we started with on Monday when we were talking about propagation of anionic chains. So this negative charge now reacts with the next monomer, specifically this resonance form of this structure. Usually we don't think about the resonance form, we just say, okay, this is a highly electronegative atom, so this is the reactive atom, the negative charges react with it. So Y is usually oxygen or nitrogen. So for example, this is methyl methacrylate, electronegative atom on a carbon atom, or acrylonitrile, so to make nitrile gloves, for example, or nitrile rubber, this is what you would use. Okay, so far so good? The rest, yeah.
Question? I kind of confused, like, the first part, the ionic polymerization, like the X, and then it goes to the Y, like what happened there?
So a vinyl monomer is sometimes written generically as just double bond X, but in the case of anionic polymerization, the X is always some specific substructure, which is usually a C double bonded to something else. So we draw it as X, where X is sometimes called the electron withdrawing group, but the electron withdrawing group is almost always C double or triple bond in the case of the acrylonitrile bonded to some electronegative atom. Yep.
So is the X here under anionic the same as the X under cationic, or did we actually just replace it with Y?
The X here is definitely not the same as it is here.
So what would we characterize X in anionic as?
The X in anionic is a carbon atom with some electronegative atom bonded to it. The X for cationic is some group that has lone pairs to donate. It's not, if it's a C double bond C, then it could be, then the electrons in the pi cloud can donate into the system. So it's either going to be C double bond C or O or N. In this case, it's never going to be C double bond C or O or N. It's going to be carbon bonded to some electronegative atom. Okay, the rest of the lecture is going to be what can we do with these structures and what are the characteristics of them. So when we draw these double arrows like this, it's not as if the electrons are literally resonating back and forth. It's that the structure is really an average of these structures. It's a way to rearrange the formal charges in a system to show you where the reactive atoms are going to be in the structure. So anionic polymerization has the characteristic that it does not terminate by itself. Ultimately, cationic polymerization will terminate by itself, but anionic won't terminate by itself. And the reason it won't terminate by itself is because it won't abstract hydrogen atoms from nearby things. The lithium counterion is never going to recombine with it. Sometimes so the only way we really terminate it is intentionally, by adding in like water. Incidentally, anionic polymerization can't be used with any electrophilic group like a hydroxyl. So the hydrogen atom on an OH group or the hydrogen atom on an acid will react with the growing chain and terminate it. So we're really quite limited in that sense, but it works really well for the materials that it works really well for. In contrast to living or to quasi-living radical polymerizations like ATRP, NMP, and RAFT, which can recombine. Statistically, it's possible for them to recombine or disproportionate. We never get that with anionic polymerization. So it's alive until we stop it. So this is truly, without any, living anionic polymerization. So the characteristics are that the chain ends are active indefinitely. All the chains grow at the same time. And it is like controlled radical polymerization, except unintentional termination can still happen in CRP. CRP, controlled radical polymerization, which means tempo-mediated ATRP or RAFT. Usually this reaction goes like a shot. Like the anionic polymerization is so reactive, as soon as you add the alkyl lithium reagent, it just goes. Sometimes you might need to cool it down, but it just goes. So you get all the characteristics of living chain growth polymerization from anionic polymerization, and you can also do chain end functionalization. You can do chain end functionalization with basically 100% yield. So if you have some chain that has a negative charge on it, and all the monomers are consumed, and all the polymer chains are essentially the same length, very close, very low dispersity, you can add in a reactant that will react with a negative charge. For example, like some alkyl bromide. So alkyl bromides react with negative charges to give you this group on the end, and the bromide floats off. Yeah.
How come we end up with the sort of the grass growing metaphor, like all the chains end up being near the same length? It's just a statistical argument, where it's as likely to add to any monomer or activated.
It's really the fact that they all initiate at the same time. Because the alkyl lithium reagents are so reactive that as soon as they see their first final monomer, they go, and what has to happen is that propagation is slower than initiation, but because initiation is so fast, even though propagation is fast too, initiation is faster. Yeah.
For functionalization to get like 100% yield, is that possible when your viscosity increases and you have really high molecular weight polymers, or is it?
So the question is, if you have really high molecular weight stuff, won't that increase the viscosity and make it harder to do chain end functionalization? This is generally done at least if you're going to functionalize the chain ends, you do it in a solvent, and you can control the viscosity pretty easily that way. So this gives you, say a polymer chain with a negative charge plus the RBR gives you the gives you whatever at the chain end. So it gives you the R group at the chain end. If you don't want to cap the polymer chain yet, you can add other monomers of other types, just like we can in controlled radical polymerization. And why would we want to do that? Because we want to make copolymers. Maybe some of us do. Okay, so imagine you want some combination of mechanical properties like elasticity and toughness, elasticity and resilience. So you want a polymer that's easy to deform, but you don't want it to break. So you want two properties where one of the components will allow easy deformation and the other one won't allow the material to pull itself apart completely. Now, one might think the easiest way to do that would be to take a polymer that has high elasticity, which means ironically a low elastic modulus, and another material that's just that has a high resilience or toughness, which both terms are energy densities that we'll talk about later, which mean resilience means the amount of energy you add to a sample before it starts deforming irreversibly, and toughness is the energy density you add to a material until it fractures. So suppose you want elasticity and resilience, or elasticity and toughness. So you take these two materials and you just pour them into the same flask or reactor and you just mix them up, and you hope that the properties, that you get the best of both worlds. Typically, what you get is an average of the two properties, not the best of both worlds, but in some cases 50% of both worlds. So we have not really succeeded. The better way to do this tends to be and the reason you don't get this is because when you mix two polymers together, for reasons that we'll talk about next week or the week after, is that polymers don't like to mix with each other. Usually one polymer likes itself more than it likes the other polymer, and there's not very much of an entropic gain for mixing two polymers, so they tend to phase separate. So if you have two phase separated polymers, then the stress will just concentrate in the elastic but brittle material, and it won't, and then the whole structure will just break. So the way that you really want to do this is to covalently tether the materials together to make a block copolymer. And this can be done using any of the CRP methods, depending on the monomer, or by anionic polymerization. So So because polymers phase separate when mixed, we often want what's called a block copolymer. So polymers phase separate when mixed. So this gives you the worst of both worlds. In terms of, say, mechanical properties. So the way to get around this is to covalently link the polymers. So if they do phase separate, they only phase separate on the nanoscale, which is usually good enough to give you the best of both worlds properties. So we covalently link the polymers to make a block copolymer. And this gives you the best of both worlds. There are a couple different kinds of block copolymers. Or let's talk about copolymers in general. We have statistical also known as random copolymers, where we might have AA, BA, BBB, A, B, A, whatever. This is random. Strictly speaking, it's not random because nothing in nature is ever really random. There will be some preference for one monomer over the other, but for all intents and purposes, it's random. So this is what you get if you combine, say you have the anionic polymerization going, but you have two different monomer types in the pot at the same time. They'll tend to add in some statistical, quasi-random way. You can have alternating copolymers. Which is just AB, AB, AB. And this occurs when a chain end with an A group is more reactive toward the B monomer, and a chain end with the B group is more reactive toward the A monomer. Then you get the alternating copolymer automatically. We achieve something like an AB alternating copolymer in step growth polymerizations like nylon 6,6, like taking diaminohexane and adding it to adipoyl chloride, which we did at the beginning to give you nylon 6,6. You have the two groups A, B, A, B. We generally don't think about those as alternating copolymers because we really consider it as like a polymer of the dimer. But it's really the same thing. It's just a nomenclature issue. Usually we talk about alternating copolymers specifically in the context of living polymerizations. But anyway, minor point. Number 3 is probably the most important, and that is the block copolymer. And there are a couple types of block copolymers. You can have AAA, BBB, which is called a diblock. And we write this as A block B. But you can also have A, B, 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 C, 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 and this is a tri-block. And we would write this as A block B block C. Or you could have 4 blocks or 5 blocks or ABA blocks. It doesn't matter, especially since anionic polymerization, as long as the flask or the reaction vessel is assiduously dry, the reaction is not going to end. You can make graft copolymers. Which you make by paying off politicians. And it's just like if you're a plant biologist, you might make a graft from one to graft one material onto another. Generally, these are made by coupling reactions, where you take some interior group and you modify it by adding another chain to it. Generally, block copolymers are not made by coupling reactions. They're much easier to make by living polymerizations, where you take the A monomers and then you add in the B monomers, because it's very hard to get chain ends to find each other. So typically, we just make them make them both de novo, where we polymerize off of the first chain with the second. And another type, which I'm going to mention and then we'll probably never see it again, is a stereo block. Where you might have an isotactic block and a syndiotactic block. The cool thing about polymer science in general is that they, except for the biopolymers, this whole world is something that human beings just kind of created out of nothing. Even the monomers have to be, usually they have to be synthesized or obtained in some process. And we've created this whole world of materials properties that, they're not metals, they're not ceramics, which, exist in nature. And metals are not that easy to get from nature because you have to smelt oxides and stuff. But I think they sort of occupy a special place in polymer, in materials science, because they're entirely synthetic. Okay, another type of polymer structure is a three-dimensional nano structure called a dendrimer, where if you start out with a trifunctional monomer, and these ones are generally made by polycondensation reactions, but don't have to be. Start out with a trimer or tetramer or multifunctional monomer in the core, and then you add one generation on top of the next to make a spherical-like nanoparticle that's called a dendrimer, which is a three-dimensional polymer. So a dendrimer is a tree-like spherical molecule which is used, for example, in for all organic nanoparticles for drug delivery. They could be used for lots of things, but for example, some dendrimer-based nanoparticle therapeutics are well along in clinical trials. And they have a nice characteristic of being monodisperse, which is a little bit weird because that just means not disperse. There's no dispersity because they're all exactly the same size. And what is the strategy that we use to synthesize these? And the more common way is the divergent synthesis. Where you start with a core and you have a branch type of molecule. And by the prime, I mean to say that this is protected and that it can't react unless it's unprotected. So the prime means protected. So in the first reaction, you have your core group. And you've reacted it with one generation of the branch group. And again, this is why you need the protection, which is usually some chemical group that won't allow further reaction. Otherwise, it would just keep growing randomly in different directions, or statistically in different directions. So this is the first generation, G1. And then I'll just draw one more generation because you can easily get the point here. And then we have A primes all over the periphery. Now, as we develop more generations, and this could be as many as 10 generations large, where you just do the deprotection reaction, then you do the next coupling reaction, deprotection, next coupling. So this is just the G2 reaction. You end up near the core of this branch structure. You end up with these cavities where you can stash things like a drug molecule. I don't know why people were laughing at that. So if you have something on the surface that can interact with a cell or interacts with something in the biological milieu, this structure can can release the drug by the, say, tumor or usually tumor. So the size and functionality used for drug targeting. And that is all I want to say about Dendrimers. And I think that's all I want to say today. Indeed. Anyone have any questions on anything I said today? Yeah.
Are Dendrimers primarily useful for the physical size of the agent, or do we sometimes attach them specific polymers that give them?
So Dendrimers can be used, are useful both for their the tunability of their sizes, the ability to chemically functionalize them in the exterior, and also the fact that they have some carrying capacity. So on Friday, we will begin our discussion of the thermodynamics of polymer solutions, and we'll start with regular solution theory. Okay, well, we'll leave the groans there, and we'll try to make it fun. That'll be the goal.